Now, what we're going to be discussing today is about 16 topics, starting all the way from a conceptual overview of blockchains to understanding why they do not have a single point of failure, the meaning of provable immutability. We're going to talk about blockchain wallets, then external private keys, multisig and cold nodes, smart asset lifecycle management, blockchain explorers, blockchain APIs, forks, which is a very, very interesting concept, blockchain consensus mechanisms, sorry, types of blockchains. Then we're going to compare briefly centralized finance, decentralized finance, and hybrid finance. We'll discuss some of the top public blockchains, smart contracts, and finally, two very important topics. What is a good blockchain use case and what is a bad blockchain use case? Shinam, as I was mentioning before you came in, please ask me the questions which you feel are most relevant to a particular topic while it's going on. Otherwise, we'll take them at the end.
Sure. Hi.
Hi. So you can just mute, but you can keep your webcam on. Okay, so let's begin with a brief conceptual overview of what a blockchain is. So as you can see right in the middle of your screen, addresses, ledger, and data. That is the core part of a blockchain. Addresses are like bank account numbers in the real world. So we use addresses to identify people. So you could even compare them to an email address, a bank account number. A ledger is a shared ledger, which means every node on the blockchain is supposed to have this data. So why do we call it a ledger? Because it's like a ledger of transactions. Who sent tokens to whom? On what date, what time, how much amount was sent, sender, recipient. Because ultimately that's what blockchain technology was invented for. Enabling the movement of bitcoins from one person to another, one entity to another. So a shared ledger is the core of a blockchain. And now along with this transactional data, we can also put other data like metadata, which describes that transaction in more detail. So at the core, we have this layer. Then what you see here, these images, they all represent nodes. A node is like a computer, a device, which is connected to a blockchain, which is a computer network. So in a very simple way, a blockchain is a computer network. Multiple nodes or computers, devices connect to it. And ideally, all of them are going to have the same data. In some blockchain layouts, that may not be the case. But generally speaking, each node should have more or less the same information. Now, these nodes, which could be even laptops, could be servers, and in the future, even normal cell phones, they are all connected to this blockchain. And then there could be.
May I interrupt you for a minute?
Sure.
Are you guys able to hear us? Because I read a comment where people can't hear. There's no volume. Can you cross check?
Are you
if
able
anybody
to hear?
Can comment in YouTube by saying if they can hear us.
Yeah. Shinam, are you able to hear it on the?
Yeah.
You are?
Yeah.
Okay, then I guess that's not an issue. So now when we look at these nodes, so let's say to this particular blockchain, there is a bank which is connected. So bank A, bank B, and then there is some company. Now each of these entities has their own internal networks, right? Where they would have all kinds of servers, web servers, database servers, caching servers. Now a bank or a corporate entity could connect this network of theirs to the blockchain through an API. So later we are going to discuss a little more about what an API really means. But API is like a service, which kind of makes it very easy for platforms to talk to each other. So if you've developed a web application or a mobile application, it doesn't actually have to be developed on a blockchain. It could be a conventional application, but through APIs, you connect it to a blockchain and it automatically can be called a DApp or a distributed app. In some layouts of blockchains which are permissioned, different permissions can be given to addresses. A classic example would be the hybrid finance blockchain or the Algorand blockchain. Now in that kind of a layout, you may have administrative nodes whose job is only to give and cancel permissions of other addresses. Then we can have validator or mining nodes whose job is going to be to validate transactions using different blockchain consensus mechanisms, something we are going to look at a little later. There are also blockchain explorers, which we are going to see later, which make it very easy for anyone to go to a website and without even logging in, sorry, you would be able to see all the transactions that have happened on that blockchain. So all these different kinds of nodes can be connected to our blockchain. So, I hope the whole audio issue is resolved.
Yes, but I haven't. Yeah,
Okay.
yes, I can read comments.
Now we move to the second point. Why do blockchains not have a single point of failure? You must have heard about this from many people. The reason for that are nodes. Because ideally every node has the same data, and that is all the data. And as long as the node is there, even one single node is still on, the blockchain is running. If 0 nodes are on, obviously the blockchain is stopped. But out of 1 million nodes, even if one is running, the blockchain continues. And later, when more nodes come in, they first download all the past data and then they start with the newer data. And that's the reason we say blockchains do not have a single point of failure. For a blockchain to fail, all the nodes have to go down at the same time, which is statistically very improbable. And even if a hacker tries to bring down the network, they should never be able to bring down the entire network, which is when we hear about cases that Solana was down for 16 hours. Now that's happened in the past, right? Entire blockchain went down, which kind of makes us question how decentralized is it? How was it that all the nodes went down at the same time? But let's not go into that for now. Now let's try to understand when we talk about a blockchain node, conceptually, what does it really have? So at the base, we are going to have an operating system. Many people think a blockchain has its own operating system. No, Ethereum is not an operating system, nor is Bitcoin, nor is multi-chain, none of them are. They need an operating system on top of which they are going to be installed like another software, right? So we say that this operating system should be hardened. Now, what do we mean by hardened? What we are trying to say here is basic security precautions have been put in place. Firewalls are there, ports are blocked. Those ports which are not needed are blocked. All the other user access and all has been controlled to ensure maximum security. Once we do that, we can say our operating system is hardened. Now it could be Linux, Windows, Mac, any of them. Most blockchains support almost all operating systems. Then we install the blockchain framework on that operating system. So example could be multi-chain. Now once that's ready, different users are going to have their keys. Assets or tokens or coins are going to be created on this. So we can say that is the third conceptual layer which comes on top of the framework. Now here you may have heard about ECDSA, elliptical curve digital signature algorithm. There are different algorithms which are used to create these keys, to sign transactions. All that happens at that layer. Then we have the API layer that we were speaking about, which makes it very easy for anyone to connect to a blockchain node and transfer data or call data in, analyze all that data. And finally, we have the application and UI layer, where your web and mobile applications can be there, which connect to the blockchain node through the API layer. Let's move on. Now, let's move on to a very interesting concept called provable immutability. So you may have heard that we say that a blockchain is provably immutable, which means you can tomorrow go to a court of law and show some data which has come from a blockchain, and the court would believe that this data has not been tampered. It has not been unauthorizedly altered. How is it that a blockchain gets this capability? Now, the most important thing which gives this capability is something called a hash function. Now, hash functions have been around for decades. They did not come only because of blockchain. They've been there forever. Now, what a hash function does, it's a mathematical function and it's a one-way function, which means we can start with, say, a word like Sanya or a PDF document or a Word document. And then the mathematical formula can calculate a 64-character hash. Now, why do I say 64 character? When we talk about one of the most popular hash functions today, it is SHA-256, and it generates 64-character hashes. So no matter what the input, a single word, say Sanya in all small letters gives us this, but the same word Sanya in capital letters gives us something different, but 64 characters. Capital S, everything else small, again 64 characters. So as you can see, irrespective of the size of the input, the output is always 64 characters. But if the input changes, the output looks different, but it is still 64 characters. I could take a 10,000 page Word document or a single page PDF. I would still get 64 characters. But the characters keep changing. So once I've calculated the hash of this 30,000 page Word document and say this is the result, I now change one full stop in that Word document and the hash changes. So in the world of cybercrime investigation where I come from, when we confiscate a laptop, we actually run the entire hard disk data through a hash function, and it gives us this 64 character code, which is then noted down on paper, signed by the witnesses. And later in court, when that laptop is provided as evidence, the court can ask for the process to be repeated. Run the hash function through and show me the code. If those 64 characters match, the court believes that the laptop data has not been tampered after it was confiscated by the police. And that is why even in the laws like Information Technology Act of India, hash functions are actually defined and a lot of legal value is given to them. So that is the first thing that gives the blockchain provable immutability. The second thing, of course, before we go in, let me just briefly tell you, when you looked at these hashes, now you may wonder that they are looking like alphanumeric code. What are they actually? Actually, they're just numbers. As human beings, we use decimal, right, which is 0 to 9. And then 10, 11, 12 goes like this. In hexadecimal, it's 0 to 9 it looks normal. 10 is represented by A, 11 by B, and like this, it goes all the way to F. Hexadecimal is just a way of numbers like decimal or binary is. So binary is 0 to 1. Decimal is 0 to 9. Hexadecimal is 0 to 15. So we say F. Right, so the hashes you are looking at are actually just numbers. And obviously, almost everything that you see in the world of computers, usually a lot of it will be running on hexadecimal. Then comes the final concept called a digital signature. So digital signatures are very commonly used. In fact, if you file your income tax returns online, you're going to be digitally signing them. So what happens in digital signatures is every person has a private key and a public key. Right? This is what is generated together. It's called the key pair. And this is what a private key could look like, a public key could look like. This would be the data that I'm signing. So a statement made by Bruce Lee. Now, when I use my private key to sign this data, this is what the digital signature could look like. Again, just a blob of alphabets and numbers. But in the future, at any given point of time, you can verify that I have signed it because you will use my public key, which everybody in the world has. You can take this signature, take this data, take this public key, provide it to the software, and the software replies to you true or false. So my private key is only with me. My public key is with the whole world. The data is obviously with the whole world. The signature the whole world has. The verification can be done using my public key. So I sign with my private key. Anybody verifies with my public key. And digital signatures is another very, very important concept which gives blockchains provable immutability. Now let's go a next step. That in a blockchain, we have so many different transactions. So is every transaction going to be signed? If there are 10,000 transactions, will 10,000 hashes be stored? Now that is where another very interesting concept comes in, which is called a Merkle tree. So let's say in our blockchain, we have 4 transactions, right? Transaction 1, 2, 3, and 4. Now, what does each transaction really have? So a transaction is something which is digitally signed by the creator's private key. So if I am sending money to you over the blockchain, let's say I'm transferring Bitcoin, I would be generating a transaction which has 4 things. My address, your address because you're the receiver. What is the asset I'm sending you? In Bitcoin's case, it's only BTC. But in Ethereum blockchain, it could be BAT, it could be ETH, it could be so many other cryptos. And what is this quantity? 5, 10, 20, 2.55. What is the quantity I'm sending? So example, this is what the sender's address could look like, the receiver's address. This is what the asset could be, say Sanya coin as an example, and let's say we are sending 25. So like this, all this is one transaction. So let's say there are 4 transactions. Now obviously 4 transactions means we calculate 4 hashes out of it. Now what we do is, instead of storing all 4 hashes, We take hash number 1 and 2, concatenate it to each other, and then hash it again to get one hash. So transaction 1 and 2 gave us 2 hashes, which when put together gave us 1 hash. 3 and 4 gave us 3 and 4 hash. Concatenated gave us this. Then we added these two together. And when we added them together and again hashed, we got 1. So irrespective of how many hashes we started with or how many transactions we started with, there could be 10,000 transactions. But when we go up the Merkle tree, we are finally left with 1 hash, which is called the Merkle root. Once you calculate the Merkle root, if even one of these transactions is tampered, the Merkle root fails. And the system immediately comes to know a transaction has been unauthorizedly tampered with. Now, let's go to the next step and see what proof of work is. Because ultimately, when we talk blockchains, the first blockchain in the world was always Bitcoin. And it is the most important. And it runs on something called proof of work. So what is this proof of work and how does it fit into the whole concept? So let's take an example here. Proof of work was originally created as a way of reducing email spam. It was not created for cryptos. It was created for reducing email spam. So what this person did in the early 90s is came out with this idea. He said that, look, a spammer can click a button and send out millions and billions of emails. How do we slow him down? Suppose we make the sender do some work. Basically, his computer has to do some mathematical calculations. When those calculations are done, some result comes. It is proving that he has done some work. And because this work will take some time, it will slow down the spammer and he won't be able to send so many spam emails. That was the basic logic. So let's take an example. What the logic is that whenever an email is being sent, firstly, there is a sender's email, which you can see here, sanya@example.com. There is a receiver's email, samaira@example.com. Then there is a timestamp. So, we can convert date time into a Unix timestamp. And then at the end of it, the sender has to calculate a number. Let's call it a nonce. That number can start with 0, go 1, 2, 3, 4. It can be as big as it needs to. But the logic is when all these 4 things, the sender's email, the receiver's email, the timestamp, and this nonce, when they are all put together, and of course in the middle we have this small delimiter, this triangle looking sign which separates these. When this entire string is passed through the hash function, the resulting hash should begin with 4 zeros. Random, I'm just saying 4 zeros. So when I take this first example, and we can see that, okay, for this, the nonce is 0. When I put it together, run it through the hash function, I can see the resulting hash is not beginning with 4 zeros. It is beginning with 6D64. So no, 0 is not the nonce for this string. Then we increase it to 1. Again, we see it is not 4 zeros. Now the sender's computer keeps trying every nonce, 0, 1, 2, 3, 4. Finally, it reaches 161,000, and that gives us a hash starting with 4 zeros, which means for this particular email, the nonce which works is 161,000. Now, as the sender of the email, somewhere I will also send this nonce, and you as the receiver will check. Your computer will put all this together, and if the hash begins with 4 zeros, you will accept the email, otherwise the email will be deleted as spam. So as you can see, there can be infinite nonces for any given string. It's not like only 161,000 works. If we keep going ahead, many more will work. We just need to calculate the first. And calculating this nonsense is not easy. It takes time. We have to do so many calculations. But the receiver only checks one nonce. So computing the nonce is considered non-trivial. Verification is very trivial. It takes some micromilliseconds. Now, for this particular example email that we were giving, if we start to calculate nonces, we realize lots of them actually give 4 zeros. We caught the first one at 161,000, but then the next one at 202312 also gives us 4. Like this, I made a small list of nonces. Actual list will be infinite long. But as a sender, I need to just calculate any one nonce. which when concatenated with a string gives us a hash with 4 zeros. Of course, in your algorithm, you can change it to 5 zeros, 6 zeros, 10 zeros, 20 zeros. Doesn't matter. So that's the concept of proof of work. Let's take a practical example. If we were to embed this into an email, of course, nobody in the world really uses proof of work for emails. It was invented for it, but nobody really ended up using it. But Bitcoin started using it, which is why we are kind of studying it in detail. Now, today, if you look at a Gmail email which comes to you, and you look at the headers, you realize that there is a message ID, there is some date, from and to is there, subject. Then there are 3 validators: SPF, Sender Policy Framework, DKIM, Domain Key Internet Management, and we can add, if Gmail wants or you want to set up your own email service, you could add a POW or a proof of work. And there you could say, okay, for this particular email string, 89804 works. Whoever receives that email, they would say, okay, this is the message ID, this is the sender, this is the receiver, this is the timestamp, and 89804 as a nonce gives us 4 zeros, accept the email, otherwise trash the email or put it in spam. Now, finally, we also come across a very interesting concept called double spending, right? So when we talk about blockchain, this is the most important thing. Now, before blockchain technology was invented, why did we not have such kind of a digital currency which no bank needed to run? The reason was double spending. Today, when I have a currency note, I can only spend it once, because once I give you that note, it's gone. I cannot spend it again. But suppose I give you a Word document saying, I owe you 100 rupees. I give you the Word document, you can copy paste it and make 100 copies. Does it mean I will pay you the money now 100 times? Illogical, which is why virtual currencies didn't really pick up, because there was no way to do it technology. But in Bitcoin blockchain, for the first time in the world, we got a way of preventing double spending without needing centralized authorities like banks. And that is the basic innovation of Bitcoin. Now let's put together all that we have studied so far into seeing how does a proof of work blockchain like Bitcoin actually work. So let's say our blockchain started some time ago. So every blockchain starts with block number 0. Then it goes 1, 2, 3, 4. And that first block is called Genesis block. And just like the universe was created with the Big Bang, if you believe in the Big Bang theory, well, then we say at the time of the bang, the laws of physics did not exist. As the universe started to be formed, the laws of physics came in. Similarly, when a blockchain is at block 0 or the Genesis block, there are no laws, there are no rules. The creator can put anything. After that, once the blockchain starts, then the rules which are put in the first block have to be followed, and you can't really change them. So let's say our blockchain has already progressed to block number 17. So what do you mean by block? So a block contains some information, and then the block header contains 4 pieces of information. Hash of the previous block. That is why we say, it's a chain of blocks. They are connected to each other. So block 17 knows who is 16, thereby knows that, okay, what is the hash of 16? That is the first thing. Second, what is the timestamp of block 17? When was it actually mined? Then the transaction root. So let's say in this block, there were 4 transactions, 1, 2, 3, and 4. We hashed them. We did the Merkle tree. We finally got the Merkle root, and only the root is put into the header of the block. Once these 3 things are there, the miner can now calculate the nonce. The same way we were calculating nonce for emails, the miner calculates the nonce here. Takes the previous hash, takes the timestamp, takes the transaction root, now calculates a nonce 0, 1, 2, 3, 4. And the moment he finds a nonce, which when added to this string gives the specific number of zeros, he says, I have mined the block. And now he can broadcast this nonce to the whole world. Of course, in reality, there are a few more complications, but for the concept, this is enough. Now, in Bitcoin, it may not be 4, it may be 20 zeros, it may be 15 zeros, but it's the same logic, a number of zeros. So in Bitcoin, we say that an average block takes about 10 minutes to mine. Why do we say that? Because again, in the Genesis block, those rules are written. An average block should take 10 minutes. Why 10 minutes? Ask Satoshi. Whoever invented put in those rules. But can we really be 100% sure every block takes 10 minutes? No. Nonsense can never be predicted. So it's possible one block takes 1 minute, another takes 60 minutes. Every 2 weeks, again, certain number of blocks specified, which is approx every 2 weeks, the system looks at the past and says, how much time did it take on average to mine one block? Suppose the answer is 11 minutes. Then the system says, no, this is too difficult. It reduces the difficulty level by reducing the number of zeros. Again, watches for 2 weeks. How much time? 8 minutes. Oh, it's become too simple. It now increases the difficulty level by adding more zeros. So like this, the system keeps checking every 2 weeks to maintain an average of 10 minutes per block. And because of this entire mechanism, all blocks are ordered, they are timestamped. Every block knows the block before it, now comes to know the block after it. So 16, 17, 18, they're all connected to each other. You cannot do double spending because once you send the token out, the blockchain knows your actual balance and you cannot double spend that same money because it's all happening on one single blockchain. Everyone can see the same blocks. And you cannot modify a previous block because the hash of the previous block is there with the next block. So if you try to tamper this on one node, the blockchain can detect this. And your node realizes it has corrupted data and then it can pull the correct data. So this is the whole basic concept of a proof of work blockchain like Bitcoin. Now that we've understood how the blockchain works, let's see how we interact with the blockchain as users. And that is where the fourth concept comes in, which is a blockchain wallet. So this is what a simple paper wallet looks like. These 4 lines that you see. So what a paper wallet is, or what any wallet is ultimately, in the real world, our wallet actually contains cash or credit cards. But then you should think, what is a credit card? Is a credit card money in itself? No. When I give it somewhere, someone swipes it, there's a magnetic strip that connects through an internet device to a bank servers and then only allows a transaction to go through. Similarly, in a blockchain, we generate addresses and those are used to actually calculate our balances. So remember, a crypto wallet does not hold crypto. A crypto wallet holds your addresses and keys. When you actually go to make a transaction, it happens on the blockchain, which is why you cannot make this crypto transaction without connecting to the blockchain. So if someone steals your wallet, what are they actually doing? Getting your keys. They can then use your private key to sign a transaction and move all your crypto to another address. But remember, your crypto is never in the wallet, it's always on the blockchain. Which is why when we talk about crypto exchanges, you open an account with a crypto exchange, they don't give you your own private key. Your crypto is kept in their addresses, which is why if the crypto exchange is hacked or runs away, your cryptos are gone. That's why we say not your keys, not your coins. In a paper wallet or in many other wallets, because you control your own private key, it's called a non-custodial wallet. You have custody of your own keys and it is always considered the safest. So in Bitcoin's example, we usually generate 4 things. First, a public-private key pair is generated. A smaller version of the public key is called the address, which you can see here, and that is what you send to the whole world. And a smaller version of the private key is called WIF or wallet import format, used in certain softwares only. But if my private key is with someone else, my crypto is gone. Let's take another example of how we can create a Bitcoin wallet, paper wallet. So you can go to a site called bitaddress.org. And the beauty is it's a JavaScript based thing. So you don't have to do it on their website. You can download the web page, the JavaScript file, disconnect from the internet, then open up the UI and just randomly move your mouse around. Now every human being will move the mouse in a different pattern. Based on the pattern, random numbers are generated, algorithm is run, and a public-private key pair is generated for you. So as of right now, you can see it's 12%. So as I keep moving the mouse around, it will keep increasing this. When it reaches 100%, it will say, okay, done. I have created a new wallet for you. It says, this is your address, share it with the world. This is your secret key. So don't share it with anybody. Keep it for yourself only. And so this is what you would write down on a piece of paper or take a printout, lock it, store it in a few places. But remember, if you lose your private key, or you delete it by mistake and you don't have a copy, your crypto is gone. Trust me, I've made that mistake. You delete your private keys, you can see your crypto on the blockchain, but you can never get it back. It is not like a bank account where even if you lose your password, the bank can reset it for you. There is no bank here. Nobody can get it back for you. Then we have other kinds of wallets. So let's take an example of something called as the MetaMask wallet. So MetaMask is a browser extension which you can download for free, very, very popular. And once you open it up, you can create multiple accounts in it. Then it can show you for each account what your balances are. Again, remember the balance is not in MetaMask, it's lying somewhere else. So in this example, it's showing me my ETH balance. So it's connected to the Ethereum blockchain and got the balance for my account number, which is here. And it says, okay, you have 0.0269 ETH as a balance, which is say $81 on whichever day this was calculated. Now, I can easily use it to send and buy crypto. More importantly, I can connect to multiple blockchains. That's a very important concept. So as you can see here, Bitcoin is not in the list. So you cannot use MetaMask for your Bitcoin as a Bitcoin wallet. Bitcoin has a separate type of wallet. MetaMask runs multiple, like it can handle Ethereum, Binance Smart Chain, Matic, few blockchains it can handle. So if we change our network and if we change to Ethereum mainnet, then it says, okay, you know what? You have so much ETH and you had BAT, but right now it's zero. If I click on say Matic, then it will show me my balances on the Matic blockchain. So with the same wallet, I can connect to multiple blockchains and see my balances and make transactions. Then I can also have a software or a mobile app like Trust Wallet. Now this one wallet supports 1 million assets. All sorts of tokens, NFTs, more than 1 million of them are supported. And as you can see here, it supports 53 blockchains. Actually, there are more than that in the world. But Trust Wallet supports 53 of them. So like this, you can use different wallets depending on what you're trying to do. And like MetaMask will not support Solana. So for Solana, you need a separate wallet. So that is a kind of a pain factor today. You don't really have one single wallet which supports every single crypto in the world. But I'm sure over time, maybe things like those will happen. Then you can also have a hardware wallet, costs more, but it's quite safe. It's like a pen drive, as you can see here, connects through Bluetooth to a mobile app, and then you can do your transactions. So again, your crypto is not in the wallet. The address, the keys are there. And that is what you would use to do your transaction. So out of all these options, paper wallet I would consider is the safest and it's free. Hardware wallet would come second in terms of safety, but yeah, it costs money, and if you end up breaking it, you may be in trouble. So you need to copy down your secret key and keep it safe. Software wallets would come next. They're kind of easier to hack in. And then of course comes the crypto wallets, which are the exchange wallets, which are the most unsafe because it's under someone else's control. As long as the crypto exchange is there, no problem. But if something happens there, your crypto is gone. So, recently on Netflix, there's this documentary about the founder of a Canadian crypto exchange who came to India on a vacation and then died. And everyone's crypto is lost because he was the only person who had the keys. Of course, in the documentary, they're saying maybe he's lying and he's not even dead. But that shows you the risk of putting all your crypto with a crypto exchange. Now let's go to the next topic, which is external keys, multisigs, and cold doors. Now, external keys are a very interesting concept. It is a non-custodial address, which means your private key is not stored on a blockchain. So in blockchains, we can have two keys types, custodial, non-custodial. Custodial means your private key is also there, which is what happens in a crypto exchange. You as a normal user log in through username, password, do an OTP. Exchange recognizes who you are, allows you to make transactions with your private key, but they have the private keys. In a non-custodial format, you have your own private key. So in a MetaMask, in a Trust wallet, in a paper wallet, you would have your own. So you can easily create this key and keep it with yourself. So we call these external keys. Then we have multi-sig. Now in that example of the Canadian exchange I just told you, supposedly only one guy had the keys. That's not the good thing. Always when you have a large amount of crypto, multiple people should control it. So you can create a multi-sig key. So we can say 3 users, 2 of them have to sign for a transaction to go through. So when we create it to the blockchain, we could run a command like create multisig, and we could say n required. That means how many are required? 1, 2, 3. So we can say, let's create a multi-signature address which has 10 keys. Any 6 of them are needed to sign a transaction. So exchanges and other large holders of crypto do that. And then finally, you have cold nodes, very interesting concept. That means a node connected to the blockchain, but actually need not even physically connect. So it can be disconnected from the internet. So let's say you hold a huge amount of crypto. So you could actually have a node running on a laptop which has no internet access. Whenever you want to sign a transaction, you open that laptop, type a few commands, generate a transaction, take it on a pen drive, go to another computer which is connected to the internet and broadcast your transaction. And then it is broadcast to the world and goes on the blockchain. But your private key is on a cold node which is disconnected from the internet. So that is something we have in the hybrid finance blockchain also. Then let's talk about smart asset lifecycle management. Now, what do we mean by this? So on the blockchain, when we create an asset, we call it a smart asset, because once you create it, you don't need intermediaries to run it, right? The blockchain automatically, based on whatever system is running, can handle all sorts of things. So, if people want to transfer it to someone, atomic transfers, you want to destroy it, you want to quarantine, all that can happen. So on a typical blockchain, so this is an example again from the hybrid finance blockchain. When we create an asset, we have a lot of metadata about it. So we can see there is a name. So WUSD, so wrapped US dollar. There's an issue TXID, which means the transaction ID. That is the transaction in which the asset was created. Everything that happens on a blockchain generates a transaction ID. And anybody can know what's actually happening. So we can see that. Then the blockchain automatically generates an address or a number, reference number for each asset. So 89-266, whatever, it generates it on its own. You don't have control over it. Then it supports multiples of 100. Units can go to 2 decimal places. Open true means you can create more in the future. Restrict means, are there restrictions on sending, receiving, or issuing this token? Then you can have details. Who is the issuer? What is the name? So Hi-Fi Bank as an example. It's a stable coin, so you can put that as a type, category. Then where is the proof of reserve? So for example, USDT, Tether issues stable coins. Where is the proof how much money they have in their bank against the stable coin issued? That's where that URL can be put here. And then you have issue quantity, you issued so much to start with. And raw means we've added 2 more zeros because it has supporting 2 decimal places. Of course, you can have 10 decimal places. Now, once this asset is created, it is in an address. Only someone with permission can issue or reissue, which means make more in the future. Once you have it, you can transfer it to someone. You can do a one-way transfer, just send it. Or you can do an atomic transfer. So if you have used a DEX like Uniswap, that does atomic transfer, where you create a liquidity pool of 2 cryptos. And only when one crypto is paid, then you get the other. So you can't run away halfway through a transaction. So what an atomic transfer does is, let's say we are now paying INR and getting USD. What the software will do or the blockchain will do is lock your INR, lock the other person's USD, then transfer, then unlock both. So the transaction cannot go one way and stop. It has to happen full. It cannot fail like a bank transfer or a credit card transaction. It either goes through full or fails. Escrow is when a crypto is locked up, say as a bank or because of a commercial transaction. Only when the transaction is complete, you can open it up. So in that case, somebody would be a third party custodian. The crypto would be escrowed with them. We create a multisig with say 3 addresses. One person, one businessman and second businessman have entered into a deal. Now this guy says, I will pay you crypto only when the product you're giving me has reached me. So there are 2 people, but they don't trust each other. So a third party comes in, creates a new address, the crypto goes to that address. Any 2 people are needed to sign and move the crypto. So sender, receiver, and the custodian. When the custodian is convinced, yes, the goods have been shipped, he and the receiver can sign the transaction and the crypto moves. Then you can burn cryptos, which means you can destroy them. We'll come to that a little later. And if there is a fraud in some blockchains, you can quarantine or block, like you freeze a bank account. This happens again on Hi-Fi blockchain and Algorand. Then let's briefly look at blockchain explorers. So a blockchain explorer makes it easy for someone to just go and see what are all the transactions happening on a blockchain. So let's take an example. So let's say I have put this address and I go to the Bitcoin blockchain explorer and put the address. Now, suddenly it says there are two blockchains with this. And you're wondering why? This is a Bitcoin address. Well, because Bitcoin forked into two few years ago. I'm coming to that concept soon. And two blockchains, one called Bitcoin, one called Bitcoin Cash, were created. And that is why we see it like this. It's not like in all blockchains you will see this. For the time being, let's just go ahead. Now that we have a particular address we are looking for, when we go to this blockchain explorer, we can see in real time everything that is happening. So we can see, oh, these are the latest blocks. And as you can see, the time is not all 10 minutes. Blocks can be very random. This one came 5 minutes ago, this 7 minutes, this 9, this 13, this 30 minutes, this 31 minutes. So, but they're in order, right? So 25, 26, 27, 28, 29, 30. Blocks are in order, but the time between them is not always fixed. Average is 10 minutes. We can see all the latest transactions here. Every transaction has a hash, what time it happened, what amount happened, all that is visible. Now I can click on any of them and go deeper. So I can go into the block. Then it shows me full data about that block, right? And it tells me what all has happened in that block. So that information shows me here that the miners of this block, how much reward they got. Let's not go deeper into that, but it shows me also the date and time of this particular block. All that information anybody in the world can see. I can go deeper. I can see difficulty level of the block. We talked about it. I can see the Merkle root of all the transactions. We spoke about this. I spoke to you about the nonce, if you remember. Well, the nonce also shows. So every block has all this. Every block has a difficulty level, a Merkle root, the nonce. All this information is here. The block reward and the fee reward. How much fees was given by the transactions in that block. Then we can see each transaction in each block, all transactions, who paid money to whom, how much. All this information is visible to us in a standard blockchain like Bitcoin. As you can see, step by step, everything is visible to us. Even if we look for Ethereum, it's just a different blockchain explorer. We go to Etherscan and it again shows us the same information. The transaction hash, the block number, same thing, the from and the to. One very interesting thing which you may notice here is we can even embed messages. So if you look at this transaction, specifically I've taken it because some time ago, the Poly network was hacked. The hacker who stole all the crypto from Poly network later returned it. But before that, he communicated with the project through the Ethereum blockchain by making transactions where the value was 0 Ether, but a message was put. So for example, he actually put this question: what if I make a new token and let the DAO decide where the tokens go? He actually posted this to the world. Now we can't see his email address because he has put this on the blockchain. The message is there forever. Even right now, if you go to Etherscan and see this particular transaction ID, you will see the message. So you can actually use blockchains to communicate. But once you put the message, it is there forever. So some people even put love letters inside messages. You can put your wedding engagement vows inside a message. In fact, you can even send emails over the Ethereum addresses. I'll make a separate video on that. Then let's move to the 8th point, which is blockchain API. And as I can see, we have crossed 1 hour, but let me continue. Almost there, yeah. So when we talked about these paper wallets, right? I generated them to a software which I built. But how is that software communicating with the blockchain? That happens through an API which looks something like this. Now, if you're a developer, you will instantly understand that this is very basic API. Blockchain APIs are like regular APIs. So you can develop your app in any software which is of your choice and then connect to virtually any blockchain using APIs. So don't get scared that as a developer, I cannot integrate blockchain into my apps. No, you can. You don't need to learn anything about blockchain. You just need to integrate the API. And of course, each blockchain will have its API documentation that when you send this command, this happens. Once you've read that, you can easily integrate blockchain into your apps. So don't fear that. It's very easy for anyone to do it. Then we have a concept called blockchain forks. Soft fork is one where after the fork is done, the blockchain doesn't break into two. It remains one blockchain. So it's usually a software kind of an upgrade. A hard fork is one where after that happens, the blockchain breaks into two and becomes two independent blockchains, both of which will continue to exist. So the Bitcoin Cash example I gave you earlier, what happened was in July 2017, Bitcoin miners representing more than 80% of the computing power said, let's incorporate SegWit technology, segregated witness, a technology to make Bitcoin more scalable. Many people said no. So on 1st of August 2017, these people who did not want the tech upgrade initiated a hard fork and Bitcoin Cash was made. So at the block number, which you can see here, 478558 of Bitcoin, the Bitcoin blockchain broke into two. Anybody who had one Bitcoin at that time automatically got that much Bitcoin Cash for free. So even I remember getting a small amount for free. And that is why, because they are forked from the same, a Bitcoin address and a Bitcoin Cash address is the same. The same address works on both. And of course, initially you got the one-to-one free. After that, you don't get anything free. And now both the blockchains run independently of each other. That's a blockchain hard fork. Ethereum also forked long ago. And we have Ethereum, ETH, and Ethereum Classic, ETC. Then we have consensus mechanisms. How does the blockchain actually do its magic? That's consensus mechanism. So we spoke about proof of work in detail. Proof of work is where the miners are solving mathematical puzzles. Their expenditure is electricity and computational power. They calculate these nonces and hashes. That's proof of work. We saw it. Now, a more preferred one is called proof of stake, where users lock a number of coins as a stake, and then you get validation rights for a new block. Now, Algorand runs on it, and Ethereum, why it's in the middle here. As of today, Ethereum runs on proof of work, but it is going to move to proof of stake once the merge happens, which is expected in 2022. I don't know whether it's actually going to happen on time. The benefit of proof of stake is the energy consumption is next to zero, whereas proof of work requires huge energy. But another point to remember is proof of work is the only one that has been tested over 10 plus years ever since Bitcoin started. Millions of people have tried to hack it and not succeeded. Other algorithm methods are not tested, they're fairly new, so only time will tell whether they are actually good enough. Then there are so many others, more than 80 of them are there. Some of the popular ones I've just mentioned here, but there are many, many consensus mechanisms which you can read about online. Let me briefly tell you the types of blockchains. A public blockchain is like Bitcoin. Anybody can go and access it, put a node to it, run an explorer, no questions asked. Private blockchain, on the other hand, would be run by, say, one organization, one government entity, only for private use cases. Hybrid blockchain could be something run by a group of banks between themselves only, not allowing other banks to access. So public, private, hybrid. Then blockchains can also be permissioned or permissionless. Bitcoin is permissionless. You don't need anyone's permission to connect and do whatever. You can mine, you can send, receive. Permission, an example would be hybrid finance or Algorand. Each address has permissions. Assets can be quarantined or locked if you're trying to commit a fraud. So there is going to be some administrative committee which controls that blockchain from an address permission point of view. Then let's briefly look at the difference between centralized finance, decentralized finance, and hybrid finance. Now, centralized finance is the conventional one, like your today's banks and stock markets. Decentralized finance is the kind of stuff that today, for example, happens on a Ethereum. Hybrid finance is what the hybrid finance blockchain and Algorand and others are trying to do, where we are trying to take the best of central and decentralized. So when we look at things like KYC, banks cannot function without KYC or know your customer. So centralized and hybrid both have it, but decentralized doesn't have it, which is why banks and all don't use public blockchain. Anti-money laundering, which means converting black money into white money. You need to check that. That's a very strict law in all countries. You can go to jail for so many years if you do money laundering. So centralized and hybrid again supports anti-money laundering checking. Then do you want terrorists to use the blockchain? No. So you have a thing called CFT, countering the financing of terrorism. Again, DeFi doesn't handle that. Then you have grievance redressal. What if your crypto is stolen? Consumer protection. in the conventional world, you can do virtually nothing. You make a mistake and send it to the wrong person, your crypto is gone. Someone hacks your account, takes your crypto, it's gone. But in hybrid finance systems, you can have these governance bodies which can get your crypto back for you. And that's one of the biggest advantages for hybrid finance. Insurance cover, so banks, whatever money they hold, there's an insurance cover so that tomorrow if a hack happens, fraud happens, you get your money back. Not there in DeFi. Regulatory certainty, which means you know what the government is going to think about it, there in central and hybrid. And finally, predictable transaction fees. That's a very big problem. In blockchains like Ethereum, you can never predict what the transaction fee will be. It could go up, could go down. But in the central world and the hybrid world, you always know what the transaction fee is going to be. Let me quickly go to the top public blockchains. So I'm a blockchain developer and architect, and these are the 16 blockchains that I've worked on. Now, they have their own merits and demerits. So if I was to look at Algorand, what I like best about it is hybrid features. So, you can quarantine assets if someone tries to commit a fraud. What I like about Avalanche is anybody can go and spin up their own blockchains. Very, very fast. Transaction speed, transaction finality, throughput, they're very high. I'm not saying the highest in the world, but they're much higher than, say, even a Polkadot or a Bitcoin or Ethereum. Binance, one of my favorites. So Binance actually runs multiple blockchains. The first is Binance Chain. That's for optimized for trading. The second one is Binance Smart Chain, which is for assets. And now they're coming up with a third one. I like it because it's pretty secure, fast, cheap to use. Cardano, not so popular nowadays. It is, I don't get to use it much. Cello is interesting because it is the first mobile-oriented blockchain. So, basically your mobile number kind of becomes like your address, and they're working on a lot of very interesting use cases around the mobile phone. So if that's your area you want to build in, Cello is a good one. Ether, of course, Ethereum is the big boss. I have separate videos on that and you can go through in depth. Phantom is pretty popular again. Polkadot, what I like is it's a network of blockchains. They have a relay chain which handles finality, and then they have multiple parallel chains. So for each use case, there's a separate blockchain. That's a thing I've taken for hybrid finance. I got the inspiration from Polkadot. Polygon or Matic is a famous project. It started out as a way to make Ethereum transactions faster, cheaper, but now it also has its own blockchain. Solana, I was a big fan, but then it's faced a lot of tech issues, so I kind of try to stay away from it. Stacks is super interesting. So, people think that Bitcoin can only do Bitcoin transactions. No, it can handle DeFi. It can do fast transactions. That's why in El Salvador, you can buy hamburgers in, say, McDonald's using Bitcoin, because transaction speeds are that fast when you use something called the Lightning Network. So Stacks is a blockchain, which is kind of like a second layer to Bitcoin you can consider. And it allows you to do DeFi, NFT, and other smart contract use cases on Bitcoin also. So I would strongly recommend read up on this. And Stellar used to be very popular a few years ago, not really so much anymore. Terra is doing very well. And in the world of decentralized finance, it's like in the top 5. I think right now it's at number 2 in the world, just after Ethereum. So my advice to you is, if you are just getting into blockchain, I would strongly recommend start with Binance Smart Chain, and then also look at Cello, Ether, of course, there's no doubt about it, and have a look at Polkadot and Terra. These are the most important ones you should be keeping in your mind. Let's quickly have a look at smart contracts. So smart contracts are neither smart nor contracts. They're just a term. In some blockchains, they are called smart filters. In some, they're called smart contracts. Forget the name. When we want to create, I'm going to give you an example of an ERC20 token, right? So that's a fungible token on Ethereum, Binance, and you don't have to write the code from the beginning. Just go to Open Zeppelin. They have a wizard. Go there, enter the name of your token. I've just put my name. Enter a symbol. I've just put ROA. It says, do you want a pre-mint? So we'll come back to that. And then it shows you a lot of options. And all you need to do is tick, tick, tick. So when I entered the name, this line got generated. And all this happens automatically. So it's creating the code for you. And the contract template is here, ERC20.solve. So they prepared very secure contract templates. Now, Once I enter this amount 250, I can immediately see here, this 250 is entered, 10 decimals is entered. Now all this is happening automatically. I'm just clicking. Now I can click mintable. When I click mintable, I see a new line is added here and a new contract called ownable.sol, solidity, that's why SOL, is also imported in. So I am not writing anything else, I'm just ticking. What does mintable mean? More units of this can be made in the future. So we start with 250 on day one, that's the pre-mint, and then we can have more being minted. Similarly, we have many other options. So burnable, that means you can destroy tokens. Binance is a classic example. Binance started off with 200 million BNB. Every 3 months, they burn or destroy some to increase the value and reduce the supply. Finally, when they have only 100 million left, they will stop burning. So do you want your token to be burnable? Then you would have ticked on this. So similarly, do you want it to be paused if some scam happens, fraud happens, hack happens? So all these kind of various options, we can just tick. The contract files get pulled in, all the data gets written here, and then few clicks later, you create your own token on Ethereum or on Binance. And that's actually how easy it is. Of course, when your use case is complex, then you would need to write custom contracts. But if your token fits into all these common things, and honestly, most projects come under it, in that case, you don't need to bother and you can easily use this. This is an example of, then there are certain other features at the bottom which you could take and just keeps creating that for you. Finally, I want to just quickly sign off with what is a good blockchain use case and what is a bad blockchain use case. A good blockchain use case, according to me, of course, involves crypto assets, not cryptocurrencies. I don't like to use that word because all cryptos are not currencies. Things like Bitcoin, Litecoin, yes, they are currencies because we use it as a medium of exchange. Then there are privacy coins like Monero. So, we say Bitcoin is pseudo-anonymous because everything about the transaction is visible on the blockchain explorer, except the name of the person because your address is only one. But if you go to a blockchain like Monero, you can't even see this, who did what transaction. So we call them anonymous blockchains, and that's why they're also called privacy coins. Then you have public blockchain natives, which is what? Ethereum blockchain, ETH is the native. Solana blockchain, SOL is the native. Now, SOL is not a medium of exchange, so we don't call it currency. We call it a public blockchain native. NFTs, non-fungible tokens. So, they could be relating to ape photographs. They could be relating to domain names, postage stamps. That's another crypto asset. Stable coins, where it's like equal to the value of, say, the US dollar. You must be using USDT, TUSD. So many others are available. Wrapped assets, where gold, coffee. Against that, cryptos are issued. So all of these come under crypto assets. Obviously, that is the best and the number one use case. Then DAOs, decentralized autonomous organizations, where a bunch of people come together who don't know each other. They pool some money and then they vote on what to do with the money. You cannot run DAOs without a blockchain. Decentralized finance cannot run without blockchain. So insurance companies, so many kinds of financial use cases, amazing. Play to earn games, where you play games and you earn characters which become NFTs, which you can sell and make money from. In-game and metaverse assets. So when you go, so for example, right now in my home, behind me, you see a wallpaper. It's on a physical wall. I have to pay for it. Similarly, if I go into the metaverse and take a home, I may buy a wallpaper for that home, but that has to be NFT. I can't take a GIF or a JPG file in. I have to take NFTs. So these are called in-metaverse assets or in-game assets. Amazing use case, and you can't do those use cases without blockchain. Then you have non-fungible tokens. Sorry, I've already covered that before, and Web 3.0. So I'll do a separate session around Web 3.0. But these are amazing blockchain use cases. And over the last several years, I've seen them succeed. But I want you to understand what is a bad blockchain use case. Almost every use case where you are trying to use the blockchain for data storage is a bad use case because the blockchains are not designed for handling data. Now imagine a blockchain has 10,000 nodes and you put data on one node. It is going to send that data to all the nodes, and that is not going to solve any purpose. which is why if the particular blockchain use case requires data, only in that case would you be actually, having off-chain storage. So on the blockchain, you're going to create the assets and put metadata, but the actual data, like an NFT, for example, would be off-chain. So if anybody talks about use cases where you're going to store data on the blockchain, I would say it's not going to work. I may be wrong. Maybe some use cases will come in the future, but as of today, it doesn't make any sense to me. Okay, I hope you enjoyed this session. Shinam, you want to take some questions right now, or do we do a separate session? Yeah.
I just have 3 questions I'll ask.
Sure.
So the Merkle root for each block only contains all the transactions in that block alone. Pair combined to arrive at the Merkle root?
Yeah. So every block, right, will have its own Merkle root because of all the transactions that went into that block only. So block 1's transactions, Merkle root doesn't have to go into block 2. I think that was the question.
Yeah. Next is for ETH chain, I have MetaMask. For Sol, I have Phantom. Same way, if I have to have a dedicated Bitcoin wallet, what would you suggest?
So actually, if you just go to the Bitcoin site, bitcoin.org, they have a very detailed wizard where you can choose which wallet makes sense. So they ask you a bunch of questions, like whether you are new to it or you're very experienced with the technology, what features are more important to you. Once you tick all that, it will tell you which wallets are best for you. There are more than 20 really good ones. So I would recommend go to bitcoin.org and run through that thing and then select the best one.
Okay, I think this is about that what is the significance of 4 zeros? Can it be any number of zeros? The difficulty level?
Absolutely, it can be. Like I said, 4 was just an example. I think you can have 10, 20, whatever you want. Any other question?
No.
Awesome. So I can see that I'm just 8 minutes overtime, which is amazing because I usually really go overtime. So I hope you enjoyed this session. Whatever questions you have, just put them below. And I'll try to do more such sessions over the next few weeks.